Chapter 12 of Science and Hypotheses. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Science and Hypotheses by Henri, PoincarÄ. Chapter 12. Optics and Electricity. Fresnel's theory. The best example that can be chosen is the theory of light and its relations to the theory of electricity. It is owing to Fresnel that the science of optics is more advanced than any other branch of physics. The theory called the theory of undulations forms a complete whole, which is satisfying to the mind. But we must not ask from it what it cannot give us. The object of mathematical theories is not to reveal to us the real nature of things. That would be an unreasonable claim. Their only object is to coordinate the physical laws with which physical experiments make us acquainted, the enunciation of which, without the aid of mathematics, we should be unable to effect. Whether the ether exists or not matters little. Let us leave that to the metaphysicians. What is essential for us is, that everything happens as if it existed, and that this hypothesis is found to be suitable for the explanation of phenomena. After all, have we any other reason for believing in the existence of material objects? That, too, is only a convenient hypothesis, only it will never cease to be so, while some day, no doubt, the ether will be thrown aside as useless. But at the present moment the laws of optics and the equations which translate them into the language of analysis hold good, at least as a first approximation. It will therefore be always useful to study a theory which brings these equations into connection. The undulatory theory is based on a molecular hypothesis. This is an advantage to those who think they can discover the cause under the law. But others find in it a reason for distrust, and this distrust seems to me as unfounded as the illusions of the former. These hypotheses play but a secondary role. They may be sacrificed, and the sole reason why this is not generally done is that it would involve a certain loss of lucidity in the explanation. In fact, if we look at it a little closer we shall see that we borrow from molecular hypotheses but two things: the principle of the conservation of energy, and the linear form of the equations, which is the general law of small movements as of all small variations. This explains why most of the conclusions of Fresnel remain unchanged when we adopt the electromagnetic theory of light. Maxwell's theory. We all know that it was Maxwell who connected by a slender tie two branches of physics, optics and electricity, until then unsuspected of having anything in common. Thus blended in a larger aggregate, in a higher harmony, Fresnel's theory of optics did not perish. Parts of it are yet alive, and their mutual relations are still the same. Only the language which we use to express them has changed. And, on the other hand, Maxwell has revealed to us other relations hitherto unsuspected, between the different branches of optics and the domain of electricity. The first time a French reader opens Maxwell's book, his admiration is tempered with a feeling of uneasiness, and often of distrust. It is only after prolonged study, and at the cost of much effort, that this feeling disappears. Some minds of high calibre never lose this feeling. Why is it so difficult for the ideas of this English scientist to be acclimatized among us? No doubt the education received by most enlightened Frenchmen predisposes them to appreciate precision and logic more than any other qualities. In this respect the old theories of mathematical physics gave us complete satisfaction. All our masters, from Laplace to Cauchy, proceeded along the same lines. Starting with clearly enunciated hypotheses, they deduced from them all their consequences with mathematical rigor, and then compared them with experiment. It seemed to be their aim to give to each of the branches of physics the same precision as to celestial mechanics. A mind accustomed to admire such models is not easily satisfied with a theory. Not only will it not tolerate the least appearance of contradiction, but it will expect the different parts to be logically connected with one another, and will require the number of hypotheses to be reduced to a minimum. This is not all. There will be other demands which appear to me to be less reasonable. Behind the matter of which our senses are aware, and which is made known to us by experiment, such a thinker will expect to see another kind of matter, the only true matter in its opinion, which will no longer have anything but purely geometrical qualities, and the atoms of which will be mathematical points subject to the laws of dynamics alone. And yet he will try to represent to himself, by an unconscious contradiction, these invisible and colourless atoms, and therefore to bring them as close as possible to ordinary matter. Then only will he be thoroughly satisfied, and he will then imagine that he has penetrated the secret of the universe. Even if the satisfaction is fallacious, it is none the less difficult to give it up. Thus, on opening the pages of Maxwell, a Frenchman expects to find a theoretical whole, as logical and as precise as the physical optics that is founded on the hypotheses of the ether. He is thus preparing for himself a disappointment which I should like the reader to avoid. So I will warn him at once of what he will find and what he will not find in Maxwell. Maxwell does not give a mechanical explanation of electricity and magnetism. He confines himself to showing that such an explanation is possible. He shows that the phenomena of optics are only a particular case of electromagnetic phenomena. From the whole theory of electricity, a theory of light can be immediately deduced. Unfortunately, the converse is not true. It is not always easy to find a complete explanation of electrical phenomena. In particular, it is not easy if we take as our standing point Fresnel's theory. To do so, no doubt, would be impossible. But none the less we must ask ourselves if we are compelled to surrender admirable results which we thought we had definitely acquired. That seems a step backwards, and many sound intellects will not willingly allow of this. Should the reader consent to set some bounds to his hopes, he will still come across other difficulties. The English scientist does not try to erect a unique, definitive, and well-arranged building. He seems to raise rather a large number of provisional and independent constructions, between which communication is difficult, and sometimes impossible. Take, for instance, the chapter in which electrostatic attractions are explained by the pressures and tensions of the dielectric medium. This chapter might be suppressed without the rest of the book being thereby less clear or less complete, and yet it contains a theory which is self-sufficient, and which can be understood without reading a word of what precedes or follows. But it is not only independent of the rest of the book, it is difficult to reconcile it with the fundamental ideas of the volume. Maxwell does not even attempt to reconcile it. He merely says, I have not been able to make the next step, namely, to account by mechanical considerations for these stresses in the dielectric. This example will be sufficient to show what I mean. I could quote many others. Thus, who would suspect, on reading the pages devoted to magnetic rotary polarization, that there is an identity between optical and magnetic phenomena? We must not flatter ourselves that we have avoided every contradiction, but we ought to make up our minds. Two contradictory theories, provided that they are kept from overlapping, and that we do not look to find in them the explanation of things, may in fact be very useful instruments of research. And perhaps the reading of Maxwell would be less suggestive, if he had not opened up to us so many new and divergent ways. But the fundamental idea is masked, as it were. So far is this the case, that in most works that are popularized, this idea is the only point which is left completely untouched. To show the importance of this, I think I ought to explain in what this fundamental idea consists. But for that purpose a short digression is necessary. The mechanical explanation of physical phenomena. In every physical phenomenon there is a certain number of parameters which are reached directly by experiment, and which can be measured. I shall call them the parameters Q. Observation next teaches us the laws of the variations of these parameters, and these laws can be generally stated in the form of differential equations, which connected together the parameters Q and time. What can be done to give a mechanical interpretation to such a phenomenon? We may endeavour to explain it, either by the movements of ordinary matter, or by those of one or more hypothetical fluids. These fluids will be considered as formed of a very large number of isolated molecules, M. When may we say that we have a complete mechanical explanation of the phenomenon? It will be, on the one hand, when we know the differential equations which are satisfied by the coordinates of these hypothetical molecules in equations which must, in addition, conform to the laws of dynamics, and, on the other hand, when we know the relations which define the coordinates of the molecules in as functions of the parameters Q, attainable by experiment. These equations, as I have said, should conform to the principles of dynamics, and in particular to the principle of the conservation of energy, and to that of least action. First of these two principles teaches us that the total energy is constant, and may be divided into two parts. 1. Kinetic energy, or vis viva, which depends on the masses of the hypothetical molecules M and on their velocities. This I shall call T. 2. The potential energy, which depends only on the coordinates of these molecules, and this I shall call U. It is the sum of the energies T and U that is constant. Now, what are we taught by the principle of least action? It teaches us that to pass from the initial position occupied at the instant T to the final position occupied at the instant T1, the system must describe such a path that in the interval of time between the instant T0 and T1, the mean value of the action, i.e. the difference between the two energies T and U, must be as small as possible. The first of these two principles is, moreover, a consequence of the second. If we know the functions T and U, this second principle is sufficient to determine the equations of motion. Among the paths which enable us to pass from one position to another, there is clearly one for which the mean value of the action is smaller than for all the others. In addition, there is only such path, and it follows from this that the principle of least action is sufficient to determine the path followed, and therefore the equations of motion. We thus obtain what are called the equations of Lagrange. In these equations the independent variables are the coordinates of the hypothetical molecules M. But I now assume that we take for the variables the parameters Q, which are directly accessible to the experiment. The two parts of the energy should then be expressed as a function of the parameters Q and their derivatives. It is clear that it is under this form that they will appear to the experimenter. The latter will naturally endeavour to define kinetic and potential energy by the aid of quantities he can directly observe. If this be granted, the system will always proceed from one position to another by such a path that the mean value of the action is a minimum. It matters little that T and U are now expressed by the aid of the parameters Q and their derivatives. It matters little that it is also by the aid of these parameters that we define the initial and final positions. The principle of least action will always remain true. Now here again, of the whole of the parts which lead from one position to another, there is one, and only one, for which the mean action is a minimum. The principle of least action is therefore sufficient for the determination of the differential equations which define the variations of the parameter Q. The equations thus obtained are another form of Lagrange's equations. To form these equations we need not know the relations which connect the parameters q with the coordinates of the hypothetical molecules, nor the masses of the molecules, nor the expression of u as a function of the coordinates of these molecules. All we need know is the expression of u as a function of the parameters q, and that of t as a function of the parameters q and their derivatives, that is, the expressions of the kinetic and potential energy in terms of experimental data. One of two things must now happen. Either for a convenient choice of t and u, the Lagrangian equations, constructed as we have indicated, will be identical with the differential equations deduced from the experiment, or there will be no functions t and u for which this identity takes place. In the latter case it is clear that no mechanical explanation is possible. The necessary condition for a mechanical explanation to be possible is therefore this, that we must choose the functions t and u so as to satisfy the principle of least action, and of the conservation of energy. Besides, this condition is sufficient. Suppose in fact that we have found a function u of the parameters q which represents one of the parts of energy, and that the part of the energy which we represent by t is a function of the parameters q and their derivatives, that it is a polynomial of the second degree with respect to its derivatives, and finally to the Lagrangian equations formed by the aid of these two functions t and u are in conformity with the data of the experiment. How can we deduce from this a mechanical explanation? U must be regarded as the potential energy of a system of which T is the kinetic energy. There is no difficulty as far as U is concerned, but can T be regarded as the vis viva of a material system? It is easily shown that this is always possible, and in an unlimited number of ways. I will be content with referring the reader to the pages of the preface of my Électricité et Optique for further details. Thus, if the principle of least action cannot be satisfied, no mechanical explanation is possible. If it can be satisfied, whence it follows that since there is one there must be an unlimited number. One more remark. Among the quantities that may be reached by experiment directly, we shall consider some as the coordinates of our hypothetical molecules. Some will be our parameters q, and the rest will be regarded as dependent not only on the coordinates, but on the velocities. Or what comes to the same thing, we look on them as derivatives of the parameters q, or as a combination of these parameters and their derivatives. Here, then, a question occurs. Among all these quantities measured experimentally, which shall we choose to represent the parameters q, and which shall we prefer to regard as the derivatives of these parameters? This choice remains arbitrary to a large extent, but a mechanical explanation will be possible if it is done so as to satisfy the principle of least action. Next, Maxwell asks, can this choice and that of the two energies, T and U, be made so that electric phenomena will satisfy this principle? Experiment shows us that the energy of an electromagnetic field decomposes into electrostatic and electrodynamic energy. Maxwell recognized that if we regard the former as the potential energy U, and the latter as the kinetic energy T, and that if on the other hand we take the electrostatic charges of the conductors as the parameters Q, and the intensity of the currents as derivatives of other parameters Q, under these conditions Maxwell has recognized that electric phenomena satisfies the principle of least action. He was then certain of a mechanical explanation. If he had expounded this theory at the beginning of his first volume, instead of relegating it to a corner of the second, it would not have escaped the attention of most readers. If therefore a phenomenon allows of a complete mechanical explanation, it allows of an unlimited number of others, which will equally take into account all the particulars revealed by experiment. And this is confirmed by the history of every branch of physics. In optics, for instance, Fresnel believed vibration to be perpendicular to the plane of polarization. Newman holds that it is parallel to that plane. For a long time an experimentum crucis was sought for, which would enable us to decide between these two theories, but in vain. In the same way, without going out of the domain of electricity, we find that the theory of two fluids and the single fluid theory equally account in a satisfactory manner for all the laws of electrostatics. All these facts are easily explained, thanks to the properties of the Lagrange equations. It is easy now to understand Maxwell's fundamental idea. To demonstrate the possibility of a mechanical explanation of electricity, we need not trouble to find the explanation itself. We need only know the expression of the two functions t and u, which are the two parts of energy, and to form with these two functions Lagrange's equations, and then to compare these equations with the experimental laws. How shall we choose from all the possible explanations one in which the help of experiment will be wanting? The day will perhaps come when physicists will no longer concern themselves with questions which are inaccessible to positive methods, and will leave them to the metaphysicians. That day has not yet come. Man does not so easily resign himself to remaining for ever ignorant of the causes of things. Our choice cannot be therefore any longer guided by considerations in which personal appreciation plays too large a part. There are, however, solutions which all will reject because of their fantastic nature, and others which all will prefer because of their simplicity. As far as magnetism and electricity are concerned, Maxwell abstained from making any choice. It is not that he has a systematic contempt for all that positive methods cannot reach. As may be seen from time to time, he is devoted to the kinetic theory of gases. I may add that if in his magnum opus he develops no complete explanation, he has attempted one in an article in the Philosophical Magazine. The strangeness and the complexity of the hypotheses he found himself compelled to make led him afterwards to withdraw it. The same spirit is found throughout his whole work. He throws into relief the essential, i.e., what is common to all theories. Everything that suits only a particular theory is passed over almost in silence. The reader therefore finds himself in the presence of a form nearly devoid of matter, which at first he is tempted to take as a fugitive and unassailable phantom. But the efforts he is thus compelled to make force him to think, and eventually he sees that there is often something rather artificial in the theoretical aggregates which he once admired. End of chapter 12.